Okay, by popular request, I thought I will do a little video showing you how you might attack some of these simple bending moment questions. So the problem that I'm going to demonstrate is the one of the frame question from the 2015 exam, question 2a. For these questions, the first thing you need to do is to get the reaction force of the structure. So by now, hopefully, you should be pretty good at doing that. So first of all, you would draw your structure out, note any unknown reactions to your structure, and then just rotate through those equilibrium equations to get your unknowns. So remember, you have three equilibrium equations, so you should be able to get at least three unknowns from your structure. And then, if you had any more unknowns, more unknowns reaction, then you need to look for some other additional special features in your structure to get them. So for this particular frame with a hinge in the middle, you could take moment about that point, one on the support, and you could, easily get the vertical reaction at the other point. Then you can use sum of vertical reaction to get the other vertical reaction. Then afterwards, you might want to consider take a free body cut of a structure through the hinge, and then you can use that hinge point to get an additional equilibrium equations to allow you to get the horizontal force. So once you've got the reaction forces, to get the shear force and bending moment diagram, I think there's the long way and the short way, so I think I'll just demonstrate the long way for you. So basically, anywhere you wish to seek the bending moment, you would create a free body cut at that location. So let's start by trying to get the shear force and bending moment diagram of this vertical bit. So let's imagine we create a cut at some location up here, and we'll call that distance to the cut as y. And if we sketch that out, we've got a horizontal reaction force of 4.5 kilonewtons here. Got a vertical reaction of 12 kilonewtons here. For this bit to be in equilibrium, this got forces are pushed to the right, so there must be some shear force pushing it to the left. And that shear force value has to equals to 4.5 kilonewtons. And if you take moment about that cut, you can see that horizontal reaction force create a counterclockwise moment. So to balance it out, the bending moment must be this goes counterclockwise, so you have to have some clockwise bending moment there. And the magnitude of that moment will have to equals to 4.5 times y. So what you note here is that the bending moment for the vertical column bit here increase linearly as you go up higher with your cut. When y equals 0, that bending moment value would be 0, and when y equals to 4 meters up here, that bending moment will be 4.5 times 5. So let me just start sketching a structure here to allow me to start sketching the bending moment. So what we have here is bending moment starting at 0, and then it grows linearly to 4.5 times 4, which is 18 kilonewtons meters. One of the other tricks that we know is that you always plot bending moment on the tail side of your bending moment arrow. So if bending moment's going that way, that means that 18 kilonewtons will be on the left hand side. So that will be the bending moment for that left hand side. So next bit that we want to do perhaps is along the beam here. And if we want to find the bending moment along the beam, we just simply make a cut along that location. So let's do that. So this time we've got 12 kilonewtons here upwards, 4.5 kilonewtons here, and we're going to call this distance x, and we've got some distribution load applied here. Okay, so obviously for this to be in equilibrium, there's going to be some shear force across that cut, so it'll be a shear force downwards, and the magnitude of that shear force as a function of x will be 12 minus 4 times x. And if we look at the bending moment, take moments about this point here, this is going to create a counterclockwise moment, this is going to be a clockwise moment. Anyway, it's kind of too complicated, so let's just call that m of x, and that will equals to all the counterclockwise moment, 4.5 times 4 plus 4x squared over 2 by minus 12x. So once you got those equations, you could, put different values in it to get the bending moment along here. So let's try putting m of 0 in this. If you put m equals 0 here, you'll get a value of 18 kilonewton meters. So in other words, the bending moment will be 18 kilonewtons in the direction of this arrow. So we do that, that means, and we always plot the bending moment on the tail side of that arrow. So that means that 18 will be on the top side, so there. And then if we substitute m equals to 3 here, you get 4.5 times 4 plus 4 times 3 squared over 2 minus 12 times 3, which happens to be 0. So in other words, the bending moment goes to 0 at the hinge as we expect. Probably a good time to draw the shear force diagram as well now. For the shear force diagram, going back here, shear force is constant at 4.5 kilonewtons. That shear force makes the free body goes counterclockwise, so it's a negative shear force. So it's just negative 4.5 kilonewtons. And when we're looking at the beam, we've got a shear force of 12 minus 4x, so you start off at 12. And this time, when x equals 0, you've got a positive 12 shear force. In other words, the shear force is going in that direction, and that direction makes the thing spin clockwise, so it's positive 12. And then by the time it gets to the other bit, it goes to minus 12. So 12 minus 12. When we get to the other bit, we start off at minus 12. Minus 4.5, and it goes up to 4.5 again. Okay. So here, remembering that the shear force diagram represents the gradient of the bending moment diagram, we know our bending moment goes from 18 to 0. So the trick is to figure out whether, and we know the gradient is changing, so it's no longer linear. It's sort of some sort of curve. It could be something like this, or it could be something like this. And the shear force diagram will allow us to figure out whether it's which way it curves. So the shear force diagram tells us the gradient of the bending moment diagram at the hinge is 0. So shear force at the hinge is 0. So in other words, gradient of the hinge is 0. And now the gradient or shear force at the corner point here is very high. So in other words, the gradient is very high. So that allows us to finish off that bending moment diagram like so. So that's the long way, and it's a way that never fails. But if you get really good at it and you're confident enough, you ought to be able to go the other way around. Once you worked out your shear force diagram, you can use the shortcut of the change in bending moment equals area under shear force diagram to help you find the different endpoints. So rather than making a cut, so for example, if you start off with bending moment 0, by the time you get up to the top, you've got a change of bending moment equaling the area under this shear force diagram. So it's 4.5 times 4, which happens to 18. That will let you know that the bending moment will be that value. And here you'll know the bending moment area, it's 18 because it goes around the corner. And then next thing you know is that the change in bending moment between this point and this point is the area under the shear force diagram here, which is half times base times height, a half